So we've reached another chapter in this gloriously complicated topic about impedance, discussion of impedance. We can talk about high Z transmission, guitars and basses and all that, and really drill into the direct box and how it functions, because it's such a important thing in both recording and live sound. So low Z versus high Z. So far, I've been talking about low Z. The modern line out gear. Consoles and compressors and EQs. These are typically low Z. Their output impedances are around 100 ohms, and their input impedances are in the thousands of ohms or 10,000 ohms. We call this low Z. But there's a whole other technology out there called high Z, and largely it's disappearing except with electric guitars. But high Z is stuff that has a output impedance in the thousands of ohms, and it's bridging into something into the hundreds of thousands of ohms. And the biggest example of this is like the electric guitar, electric basses, sometimes keyboards, and there's some cheap microphones, karaoke mics, and that kind of technology, Radio Shack crap that you might encounter out there. It's really about guitars and basses. And so this transmission, starting with this system of having really high source to really high load, has some serious drawbacks. And here's a list of them in blue here. They're typically unbalanced systems, so hum and buzz are a problem because there's no common mode rejection. So maybe that's not about high Z itself, but these systems typically are, so that's the problem. And then high Z lines are more susceptible to level loss, and so level loss, signal gets lost, and therefore a lot more gain is needed, and then the devices are even noisier. And then there's some other things here. We've talked about this a couple times, but capacitance on the guitar line, capacitance across the cable, can interact with the resistance, making a low-pass filter, which can eat away all the high frequencies on the cable, and that's a problem. So, a magnetic guitar pickup, and there's a single coil pickup there, many windings of copper wire there, very, very thin wire. The impedance of these devices is very high. It's hard for current to get through there, and the source impedance of these pickups is very high. And the typical output impedance is about as low as you get, it's about 4,000 ohms, but they can range up to 20,000 ohms. I think the Strat's 5K. And so what's going on with these things is, just to be a little nerd here, you have a metal string vibrating within a magnetic field, and the metal string kind of pushes and pulls the magnetic field, and that magnetic field pushes and pulls induces a change on the coiled wire, and the coiled wire, of course, is now moving in current, and we've got an electrical signal that can be amplified. There's another type of pickup out there. It's been around even longer. The piezo or piazzo. I don't know how to pronounce it. I'm going to admit that. I call them piezo. And the piezo pickups, they work totally differently. If you take a quartz, and other materials do this as well, but other crystals, but quartz, if you squeeze them and you pressure them, or they're sensitive to vibrations, they emit a very little tiny electrical current. And so that little animation there from Wikipedia is showing you the ranging in voltage as we squish this pickup. And of course, here's a Dean Markey, that little quartz, little piezo pickup that we would stick on a guitar. And they're very, very high impedance. Quartz doesn't want to give up its electricity very easily, and these things can be as high as 1 million ohms source impedance. So they don't like to give up electricity. And other uses for these things, you'll see them in drum triggers, you'll see them in piano pickups, you'll see them in underwater mics. All these kind of things are piezo. So they are naturally high Z. And I guess that's what I wanted to say, was they are inherently high impedance. Other issues with high Z, two conductor lines, right? I mentioned this earlier, like unbalanced is no bueno, right? The noise comes into unbalanced lines, and the shield is carrying the audio signals, so the shield, any noise that gets on the shield gets amplified, and this is no good. And capacitance, all right, this is storage of charge in an electric field, and it stores up between the conductors and your guitar cable. And this can really seriously low pass your guitar cable, and I've seen this many times in my life, where somebody plugs into a 50-foot guitar cable so they can dance around on stage, and then their guitar sounds like it's underwater. And this is because of, a low pass filter being made between the resistance and capacitance on the guitar cable. So this is pretty problematic with long cables. Things that are really high frequency, if you're dealing with a RF and data and antenna lines, you're really gonna want to avoid, keep your cables short. And of course, guitars have high Z, so they are guitars, basses, keyboards, cheapo mics, these sorts of things. They're high impedance in their source, so they are impacted by this problem. So the solution, of course, is that we cannot, the problem, to boil it down, summarize it, is that we can't take an electric guitar, stick them out in the Nescom studio, and run a really long 1/4-inch cable and plug it into the API. It's going to pick up noise, it's unbalanced, it's going to pick up the radio station, it's going to be low in voltage, you're going to need a lot of gain, it's going to be dark because all the high frequencies have been rolled off, it's going to sound like poo. So, and then also, their output impedance, which is a 5,000 ohms and up, you're going to plug them into a mic preamp, which has a source impedance of 1,500 ohms. You're going to plug 5K into 1,500 ohms. And what's that ratio? 3 to 1? That's definitely high Z to low Z, which is bad, bad, bad. So this is what the direct box is for. And here are the following tasks. I believe there's 6 of these. And these are pretty important to know. Oh, we started with number 2. That's kind of cool. Where'd number 1 go? Well, we'll just start with number 2. Direct boxes convert high Z to low Z signals. So you plug your 5,000 ohm source impedance guitar in here, out comes 150 ohm output of the DI. And it's much, much lower, and now you can run it long distances. And that's cool. Oh, there's number 1. They are high Z to low Z, of course, gets rid of noise issues, and the low Z signals are more they fight off that evil noise, and this creates a bridge relationship. Your guitar can now, by lowering it to 150 ohms, the output of the guitar once it hits that XLR jack, you can now plug that into a preamp and bridge into the preamp and get all sorts of nice advantages of bridging. And this, of course, turns the guitar's kind of almost line level voltage down to mic level, so we can plug it into the preamp. We can balance signals. Well, that's a good one, right? It goes through a balancing transformer, creates a differential output between pin 2 and pin 3, and your guitar is now balanced, and it can really benefit from the common mode rejection that the mic preamp offers. This can also create ground isolation because your ground line, pin 1 on the XLR, is not, you can just flip the little ground lift switch. It's up there in the picture there, ground lift, there it is. And you can get rid of the hum or buzz because you're breaking the ground loop. Woohoo, that's super cool. And that, of course, connects to what we talked to right before break. And then the last thing it does, number 7, is it splits the signal in 2. You can have the high Z guitar come in and a high Z guitar go out, go into the guitar amp. You can rock out on stage and still send a low Z output off to the preamp. Okay, cool. I love DIs. They're so cool. They do all these cool things. Here's a graphic to kind of show that. Okay, there's the world's ugliest guitar. That's a bass, right? So the bass is rocking away, and its output impedance is, let's say it's 20,000 ohms. Let's go right in the middle here. 20,000 ohm output. It's going to go into the DI, and it's going to bridge right out. Not bridge, that's a bad word. It's going to jump right out of the 1/4-inch output into this Ampeg bass amp. And so the Ampeg bass amp, the bass really sees the Ampeg bass amp directly because it's just going out of the 1/4-inch jack. And so that signal reflected to the bass. The amp is somewhere between 100,000 ohms to 1 mega ohms, excuse me. So that's definitely 1 to, the 20 to 200,000 ohms would be 1 to 10. So that's a pretty, 1 to 10 kind of bridged relationship. And then the XLR out connects to your mic preamp. And the XLR, there's a transformer in here on the XLR out, and it's taking this 20,000 ohm output impedance and it's dropping it down by a ratio. Typical DI is 12 to 1. So it's dropping it down by 12, which turns that into approximately 150 ohms. And it can range, 7 to 700 ohms. And that is now going to drive nicely into a preamp, which has roughly a 1,500 ohm, 1.5 kilo ohm input impedance. Oh, look, there's a couple op amps sitting right there. I like that. I've lost my mouse. There they are right there. Op amps. Woohoo. So, this signal is the impedance of this preamp is reflected back through the transformer to the base, and it creates roughly a 200,000 ohm. Once it's stepped up through the transformer, roughly the base sees about 200,000 ohms as a load on that DI. So this creates bridging from the base to the DI and the DI to the preamp, and that's why we do it.